Okay, so let's begin. We'll focus from week 9 to 12. For week 8 till 1 to 8, there were so many hands-ons done, right? So let's start with week 9 and briefly discuss things from week 9 starting onwards. I'm trying to share my screen also. One second. Yes, I think my screen is visible also. Okay, the very first concept that week 9 begins with is multi-armed robots. I have a document in hand. Let me quickly take you through the concept that week 8 ended with, that is a single armed robot. So, if we think that this is a start state, yeah. If we assume that this is a start state and this is the goal state, if we want to reach here, in case of single armed robot, we are very clear that the first step will be take out this B from here, put it down on the table and take out this D from the top of C and put it on the top of D. So single arm case, it was very clear. In the multi-arm case, there was a differentiation between deleting of clear and not deleting of clear. So this was an area of confusion. So I thought I can briefly share my understanding on that. First, I marked as delete clear. Let me explain what it means to be deleting clear. In this case, let me write if I assume two arms are here, one arm is picking up B, and another arm is picking up D. A and C still continue to be on the table. Deleting clear of X means if we pick up some block, we assume that it is not clear, and this means no block can be loaded onto its top. So if we delete clear upon picking up is same as unstacking, except that it is taken on the top from the top of a block or from the top of a table. I'm just using the word liberally. If we take up a block, we assume that when we delete the clear constraint, we say that no block can be loaded onto it. So this means this will be the first state. Then the second is we will need to put B first. This arm will continue holding D. And the third is we can put D on top of B like this. So even though we have two robotic arms here, in this case, we needed 3 timestamps because we had to wait for B to come down to the table and then only we could put D. What advantage we get when we don't delete clear is even after picking up a particular block by a robotic arm, X continues to be clear and we can load onto it. We can load other blocks onto it. So the first step would be as usual, like the first arm will pick B, the second arm will pick D, A, C continue to be on the table. In the very next timestamp, if since we can assume that pickup of B is done here, right? So pickup of B still keeps B as clear. So in the second timestamp, while B is coming from this position to this position, in the very parallel time, we can also keep loading D onto the top of B. It allows to do so. So these two actions, this B coming down and D being stacked onto B will happen in parallel. So this is the advantage. This is because we are thinking that B is still clear. So if it is clear, we can go ahead and load or stack D onto B. So that is this reduces the number of timestamps. This one assumption reduces the number of steps that we need to achieve this goal state. Obviously, C continues to be on the table. So we can also think it as mid-air stacking is possible. Or otherwise we can also write as arm can hold many blocks. Because B is still clear, arm can hold D and B together. Arm can hold many blocks. Okay, if we leave that goal state, we can see like this can be B, D. This is A, C. In that second timestamp, my state can also look like this. Since B is clear as per that assumption, this arm can put D onto here itself. While B is still in air, this arm can put onto the top of B. That is what this not deleting clear and allowing the B to be still clear gives the advantage. Just stop me if we have any doubts, otherwise I'm just continuing. Okay, I'll move ahead. So this is the very first topic in week 9. Next there were few theoretical slides like mean sense analysis and graph plan will come. Mean sense analysis, I think you can go through the theory. When we come to the graph plan, earlier we had a start state and goal state, and we were exploring different ways to reach the goal state by constructing plans, whether if it is forward state space planning FSSP, we go from front to the back, start to the end, or if it is backward search or whatever. So we started constructing plan step by step. But here, what happens in the next approach, the graph plan is we list down all possible actions that can be done in every timestamp and then continue exploring them to find a solution. So we build a very big plan and we somehow search in it from the backward direction and find a plan to do that. That is what is meant by this graph plan algorithm. What it basically has, as usual, it has a start state and a goal description. It lists down all the propositions and actions. This layer, they call it as P0. This is the action layer and this is the proposition layer. So in this layer, action layer, they list down all possible actions that can be done on P0. We can see from the state that in this state there are only 3 actions possible. With this arm, with a single robotic arm, we can either pick up D or we can either unstack D or unstack B or pick up C. We understand from our general observation of this image that there are only 3 actions possible. So unstack, unstack D, unstack B, and pick up C. This no op is nothing but we want to remain silent and we don't want to do anything. So that is no op operation. It just continues the state in whatever it is. So action 1 can be nothing also. In the next timestamp, it continues to be in whatever situation it is. So from this observation, we can easily find out what the actions in layer 1 are. And then there is the concept of mutex actions. Okay. And then there is this concept of mutex actions and mutex prepositions. Basically, when we list down all the possible actions and all the possible prepositions like this, there will be a situation that 2 actions, if one action happens, other may not happen, or 2 actions cannot be taken in a single timestamp. Even if there are two robotic arms, we cannot take up 2 actions at a time, maybe due to some constraints also. And 2 propositions need not hold true at the same timestamp. So such kind of pairs are called mutex actions or mutex prepositions. I have picked up a few questions from our PSGAs. So this question says, which are the mutex actions in layer 1? We see that layer 1 there are 3 actions: picking up D, picking up B, and picking up C. So the first option is no op and unstack B. What is no op 3? No op 3 wants to keep the arm empty. It doesn't want to do anything with the arm in this timestamp. Whereas unstack B wants to pick this B from on the top of E. these two are contradictory, right? I cannot remain without any action, and at the same time, they want me to pick up this block from the top of E also. So these two actions cannot go together. Either I'll remain silent, either I'll unstack B. So these two are said to be mutex. I have written here, if one is done, other is not possible. If I choose to keep quiet, I don't pick up B. Similarly, the second option, no op 3 and pick up C. It again says no op 3 is arm empty. If I want to maintain the arm empty, I cannot pick up C. This is also obvious. The third option is unstack BE and pick up C. The third option says take this BE, this is one action, take this C, this is one action. Both I cannot do in a single timestamp, right? Either I can do this, either I can do that. I cannot do both. So if one is done, other is not possible again. So that's why these three options are mutex. When you check the fourth option, it is no op 7 and pick up C. What is no op 7? No op 7 is I want to maintain C clear. This is not arm empty. Just note that this is C clear. I want to pick up C. This is possible. Just now we explored this way. If I, in this concept, even if I pick up C, I can still maintain C to be clear, right? Just by not deleting the clear of X. This part that we discussed just now. So with that, these two options can go. Even if I pick up C, it can still continue to be on clear state. Don't delete clear of C. Clear of C. So with that, this is possible to do have both of these actions in timestamp one. Okay. This is with respect to actions. If one is done, other is not possible. What about mutex propositions? Means they do not exist together. Proposition, you know that it is a true or false condition. The first option, if you explore the options, it will be more clear. The first option is E should be clear and arm should be holding C. All this they are talking about layer 1. Layer 1 is this one. This place is this one. This P1 is the layer 1. This P1 is achieved only with one action from P0 to P1. There are no 2, 3 actions. Only one action takes you from P0 to P1. Whatever is the choice of your action, that's okay, but only one action you are allowed to do. But for clear of E, we need unstack BA. Only this action I can do. Holding of C means I need pickup of C, right? So this clear of E needs this action, holding of C needs some other action. So two actions are needed to achieve both this. I cannot do that. And anyway, I have only one robotic arm. I can either take out B and make E to be clear, or either I can hold C. So with a single action, it is not possible to achieve both. But in this case, see, clear of B, I don't need any action. B is already clear in this state itself. So holding of C, okay, I can pick up of C. Pickup of C, single action is sufficient to achieve both these. Achieve in the sense, of course, it is already achieved. Clear of B is already existing. And anyway, if I pick up C, these two will be satisfied. Same is the case for this. If I just go and pick up C, I'll satisfy holding C. D is already clear, so I don't need two actions. But this case is not like that. For holding of B, I need some unstack operation. For holding of C, I need some pickup operation. Again, it needs two different operations, and we cannot achieve in a single transition from P0 to P1. That's why these options are mutex propositions. Give me a moment, please. Yeah, thank you. So this is with respect to mutex actions and mutex propositions. We'll move to the, I think we have another example also to make this concept more clear. Again, they are asking which of the mutex actions in layer 1. We see unstack of PQ means taking up this, pickup of R. Again, those two are different actions. And for this also I want ARM, and for this also I want ARM. I cannot do both of them together. So they are mutex. Similarly, you can explore for other options, but there is some confusion with respect to these two. Stacking of PR. So this action and stacking of RQ, they do not belong to layer 1 at all. Layer 1 only deals with whatever state the is there when the P is 0, or whatever is the start state. Stacking of R onto Q is not achievable from the start state. It needs some taking out of P from here and then putting of R on top of it. So these two actions do not belong to layer 1 at all. They come in future layers. So that is the clarification. We need to check that also. Are these directly applicable on the start state? There are mutex propositions. Clear of Q and arm empty. Yeah, clear of for the both this can be achieved with just unstack of P. We can achieve both this. Arm is oh, sorry, arm empty. If for clear of Q needs, I need unstack of P, and arm empty, I need no op. I don't want to do any operation. Only then arm will be empty. So, but there is again a mismatch, right? If I want to remain with no operation, I cannot unstack P. So this is mutex. Again, the same holding of P, holding of R. Obvious that it requires two different actions, and it is not possible. On table R, clear R, it is already there. So I can just go with no op, and it achieves both these. So they are not mutex. Similarly, on table R and on table Q, they are already there. They here also it's just a no op achieves both these. So these two are non-mutex. These two are mutex because holding P needs unstack of P and holding R needs unstack of R. So two different actions and there is a mismatch. So here we can achieve both this with a single operation. That is the concept of mutex actions and propositions. I think that's it from mutex side. Next concept that was introduced in week 9, if I'm not wrong, is AOSTAR. AOSTAR, I have taken a problem from our GA9. As you know, Avostar has this representation where two edges, if they are represented with a curve like this, it represents an AND. Otherwise, if they are just like this, it represents an OR, and we are free to choose whichever gives lowest cost for least cost for S. So how do we explore this graph and find the value for SS? We begin with exploring from S. S has, this is one side, this is one side, this is one side, and this is four different ways of getting values, and we need to explore which path gives S a smaller value. In the first one, A, they gave heuristic value of A as 40, heuristic value of B as 35. There is an AND relation between A and B. So we need to add these two values. It gives 75. In the second part, C has a heuristic value of 60. This is straightforward. While exploring, we go only one level down, not till the end. We go layer by layer. So for C, the heuristic value is 60. For D, the heuristic value is 40. There is an again AND condition between E and F. So we need to add both these values. 20, 20, it will give 40. And then it was given in the question that edge cost is equal to 2. Edge is equal to 2. So A and B, if I take, it will give a 2 from here, 2 from here. Total, it gives a, sorry, edge cost is 1, not 2. Okay, A and B, if I take, it gives an edge cost of 1 from here, 1 from here. So total, it will give another plus 2 with respect to edge cost. C will give only plus 1, D will give only plus 1. E, F, if I take, there will be a plus 2 of edge cost. So there is 77 coming from this side, 61, 41, and then 42. Out of all, these are the four ways by which S is getting the values, and we need to choose whichever is the lowest. So in these values, the lowest is from 41. So S as of now is 41. And we will explore whatever path we choose in the previous step. Here we chose D is 40. So we'll take D and explore it to next level. So D has in its next level L and M. L has a value of 70. M has a value of 80. So this the circle here represents that this is a leaf node. Its value is fixed. We don't need to explore it any further, and this is a finalized value. So L is 70 and M is 80. D has an OR connection between L and M. So whichever is least, it will take that. So 70 is lesser and it will contribute a 1 of edge cost. So D gets 71. Since it's both children are having finalized cost, D also is achieving a finalized cost. There is no more exploration in terms of D. So D, so I just circled it also. So D has a value of 71. Other values from other branches we are yet to explore. We will do only one by one. Right? So here in this case we are exploring D. So I just copied C has a 60 here, AB has 75 and EF has 40. These pluses are with respect to edge costs. Okay, see now that earlier whatever D is giving was the least, but when we explored D and finalized its values, now we turned that it has higher cost than EF. EF at this step is giving me a lesser value of 42. So S continues to take 42 from this side and it explores EF next. E and F have the same value 20, so we take in alphabetical order. In AND condition, if one is higher than the other, the tie breaking rules will be given in the question. So we are taking E to explore next. E has again two children, N and O, just like how we did for D. N and O are having the finalized cost, they are the leaf nodes. But E is having an AND relationship. We will add both these two, it will become 30, and E will get one from this edge cost and one from this edge cost. So E also achieves a finalized value of 32. F, anyway, we have not explored it at all. We have not explored it. So just we copy the value of 20 as of now. So together this is 52. D, earlier it achieved the finalized value of 71. Others are still remaining in the previously assumed values. So in this, again, EF is giving me a smaller value of 52. This plus 2 is with respect to edge cost. So the S value as of now is 54. Same way we explore this, we choose the least value from this option, right? S has four different options, this. So we choose from this. So we explore the unvisited nodes in that branch. So F is still there. As we see, F has two children, P and Q. Again, there is an OR relation. It will take from P, this is 20, and there is 1 of edge cost. It will become 21. So F also has achieved the finalized value 21. E has 32. And so together there is an AND relationship 53, and till now it is clear that S is having a 55. Why did it stop here? Because this is the branch where S chose a value, the least value, and then this branch, in this branch all variables got their fixed values. There is no scope of exploration. All are explored and they got their original values. So the algorithm stops here and we ended up at a value of S is equal to 55. But the question is this an optimal value for S? To check that, we need to propagate the values from leaf nodes to the top root node. See, if G is 40 and 20, H is 20, these are the fixed values. This means the addition will give us 60 and A will get original value of 62, including the edge costs. Even though heuristic value is 40, original value of A is 62. Similarly, for B, it will be 20 plus 30, 50, and then another 2, this will be 52 for B. Here 50 plus 2, again 52 for C. 70, this is an OR relation, we need to observe this, so it will be 71 for D. These are the actual values. There is 10 plus 20, 30 plus 2. So 32 for E, 50 plus, oh, so this is an OR relation. So F actual value is 21. If we propagate still further, this side S is getting from A and B. A is 62, B is 52, something like 114 and then plus 2. So 116, this side S is getting, and here S gets 53, and here S gets 71, and here in this EF it gets
72, madam.
55. Am I saying anything?
72.
Okay. So S has got these values 116 from here, 53, 71, 55. As I observe, 53 is the minimum value. But our algorithm didn't give 53, it gave us 55. It went in the direction of EF and it gave us 55 is the least possible value. This difference is, so we did not find optimal solution for this solution for this graph. Why it happened is the heuristic function is not admissible here. That means admissibility, as we all know, h value of heuristic value of any node should be less than or equal to its original value. H value is what is there in the circle. So h is less than, original is outside, what is written, heuristic is inside the circle. So inside value should be less than or equal to this outside value what we have written here. See, that condition is failing for C. 60 is not less than or equal to 52. So this heuristic function, whatever is giving me 60, is not admissible. Because of this reason, in the first time step, it was assumed that C is 60. Anyway, if I find, see, for all other nodes, the original value is higher, right? 40 is 62, 35 became 52, 40 it became 71. So here what the assumption was that C now itself is 60, even if I find original value, it will anyway increase, right? So the algorithm skipped the C. So that is the reason. But actually C was decreasing. So for this reason, the graph didn't give an optimal solution. So just like other A star and all, A star gives an optimal solution only if it is admissible. Not if and only if it is just it. Heuristic is admissible. Optimal will be definitely, so optimal solution will definitely be given if heuristic is admissible. If it is not admissible, sometimes it gives optimal, sometimes it doesn't give optimal solution, but that is not reliable. So that is the understanding for AO graph and its admissibility. So I think this concludes our week 9.
Madam, there is one question from
GS
Nathan
also
sir.
covered practice assignments. One is related to graph plan and another is related to AO star. They have covered
Madam,
both of
am I
those.
audible?
So can we move ahead to week 10?
Madam?
Yeah, Naren, you're audible. I think my question has been answered.
No, will it find always? Because for AO star to find one of the condition is heuristic function should be admissible. There are maybe one more or two more, I don't know.
That was my
Madam,
understanding. Yeah, go ahead.
no, in quiz 2, some problem was like this. Madam, Rajalish madam, you are able to hear me?
We can hear you. I can hear you, Naren. I don't know what.
But ma'am is not able to hear.
Am I audible now?
Yes, ma'am. Yes, ma'am. Madam, is it fair to say that if the heuristic function is admissible, AO star will always find the optimal solution?
Yes, correct. If it is admissible, it will always find an optimal solution. If it is not admissible, it may or may not.
So there is no other condition for AO star to find the best, optimal solution. Only condition is the heuristic function should be admissible. Is it correct?
As per our lectures, because for A star there were 3 conditions. We were
yes,
not
madam, that is
given.
right. In
We
quiz 2, that problem was there. Here only one condition, huh?
As per lecture, that's my understanding.
Okay, no issues.
No, there were the other 2 conditions were with respect to infinite this one and all, right? infinite state and all. So I think
State space is
here
infinite.
infinite, but here anyway it will be finite because we will
Finite.
have leaf nodes and the values. So that is one thing. What is the third condition? Branching.
There should be increment,
There,
which should be the increment should be there between the nodes.
some delta something.
Delta minimum is delta should be there. Okay.
That I'm not sure, but as per this,
So in Eostar, if heuristic is admissible, Eostar will find the optimal solution. Okay, madam. Thank you.
And also, I think the reason for that is the difference between A star and A star is where they are applied. This is applied to solve a problem, and your space is only the solution space, which is typically finite, right? Or not typically, always finite. So that is why it will always throw an answer. If the heuristic, it will always give an optimal solution if heuristic function is admissible. Whereas A star you're using mainly for a search in an infinite space, potentially or.
Okay. So doubt cleared. You can continue, madam, please. Sorry.
No, were there any interruptions earlier? I didn't hear anything earlier till now.
No, nothing. Please go ahead.
Okay, so
like if the AO star hits the leaf node, it's done. Like the algorithm stops as the AO star hits
no, not hitting the leaf node. If we hit the leaf nodes here itself, right? For D, we hit L and M, right? No, whatever path we choose to be the minimum, in that path, if every node gets a finalized value, every node gets a fulfilled value, then it stops.
Understood.
There is no scope to explore further, right?
Yeah.
Okay, week 10, there were two concepts. One is rule-based and another is rate in it. I'll recheck if it is recording. Okay. So I think rule-based is simple to understand, but I'm just quickly revising for continuity. Rule-based has this kind of expression that will be given. There are two rules in this. If we see rule 1 and rule 2, this is the working memory as they call, and each one is called an element inside working memory. So these are called working memory elements. The main aim is to see what elements in the memory fits these rules and then do some operation, RHS operation, what they specify on those elements. So that is the main goal of this rule-based approach. So I quickly took there is nothing theoretical to explain this. So I took an example. There is this concept of conflict set. Conflict set is nothing but the working memory elements that satisfies the given these two conditions. So for rule 1, they are asking what are the working memory elements that satisfies that, the rule 1. So what rule 1 says is it needs two elements first of all, because there are two conditions in this. So first one should be of this kind and second one should be of this kind. The element 1 will have some index, element 2 will have some index, element 1 will have some index and some value, element 2 also will have some index and value, but the constraint is that this index of element 2 should be greater than whatever index is there for element 1. Similarly, with respect to value, there is some condition. It should be less than. So are there any such working memory elements that satisfies this rule 1? That is nothing but conflict set. We can easily explore the options and we can find out that will be easy. Otherwise, we need to do for each and every combination. We need to put 1 here, 2 here. By 1, I mean 201, 202. If this pair, is it satisfying? No. Then 202, 203, does it satisfy? So like that we need to do. So it is better to explore from the options. From the options, we see the first one is 2 and 1. So they'll put 202 here, 201 here. This is with respect to rule 1. So they gave 2 elements. I just put it there. So for 202, what is the index? Is 1. Value is 20. And for 201, the index is 3. The value is 17. So is it satisfying? Yes. 3 is greater than this one comes here. No, this angular basis here. 3 greater than 1. 17 is less than 20. So it is satisfying. So this is an eligible element into a conflict set. Same way we I will show for one more. We don't waste so much of time on this. I'll show for this 202 and 203. This option we are exploring. What are the values for index and value for 202? This is 1 here, this is 20 here. From here I am taking. 201 has an index of 1 and a value of 20. 203 has an index of 2 and a value of 23 here. So this angular x should be considered here. 23 less than 20. So this is failing. So that is why this is not an that is not an element in the conflict set. That's how we check for the values, and we can easily get this. There is nothing much in this. Basically what happened here is we are checking each and every working memory element. The earlier we didn't so 202 and 203, when we are exploring, we need to take all the values from here, index value freshly, and again do a comparison from here to here. We didn't maintain any record that 202 is something like this. We didn't have any cache kind of remembrance when going from one check to another. So to avoid that, they put up a RETENET algorithm which stores these working memory elements into alpha nodes, what they call. These nodes represented by rectangles, they are calling as alpha nodes. What alpha nodes does is, each alpha node will have a check inside it. If a particular working memory element saves that, satisfies that, it stores that elements here inside it. So next time when you say 101, we already know that it is residing in some alpha node. So we take those working memory elements and save into the alpha nodes. We take them as deep as possible by checking the conditions that are given in the alpha nodes. This will be more clear if we work on this example. We'll try to place these alpha nodes into this. I'll choose a bright color. Yeah, the first 101, it has this in the rule-based approach. The first one is always a class representation, so it belongs to class cargo. So which direction should this is a working memory element, go? It is a class cargo, it should go here. Win, next is it for win variable, it has an a1. Okay, whatever they gave in Angular braces, it is a variable, it can be anything. Okay, it has some win value and it has some value for the variable flat. So our 101 satisfied all these three, so it should be sitting here in this alpha node. For simplicity, I'm just writing 1 because all these are 101, 1 till 109, right? So we'll use 1 to 9. Okay, one is belonging to class cargo. It has some win variable, it has some bed variable, so it came till here. Similarly, for 2, it belongs to class passenger, so our 2 should go into this. It has some win variable, fine. It has a limit of 2, so we came till here. Limit is 2, so our 2 working memory element should sit here. Next, 3 is also class passenger. Win some value is there, limit is also 2. So our 3 also will sit here. 4 has passenger, again some win is there, limit is 1. So 4 will go here. 5 is belonging to class power. So we should come in this branch. Power, for win some value is there. HP is 400. See, HP is 400 satisfies this greater than or equal to 300. It also satisfies less than or equal to 500. So our 5 should go, 5 means 105, should go into both these alpha nodes. It satisfies both the conditions on HP. Similarly for 6, power, win some value is there and HP is 800. So 800 means it should come here because we are checking greater than or equal to 700. So it will say here. And 800 is also greater than or equal to 300. Oh no, it is 6. Okay, so our 6 will be inside this also, here also, and in the, sorry, 6 is sitting in both these alpha nodes just like 5, which is satisfying 2. 107, power, some win value, and HP is 900. Yes, so 900 satisfies this, 900 satisfies this also. Okay, 108. This goes to class wheel. It has some win and tire is regular. Okay, so this is the only alpha node where 8 sits. 9 goes to wheel, win, and tire is slick. So 9. Yeah, so this is the position, these are the positions of all our working memory elements inside this rate and it algorithm. By saying this, it is obvious that 2, 3 have something in common and 4, 6, 7 has something in common. So that kind of ideology this algorithm provides, which is different from what the earlier kind of representation. What happens after we take all these WMEs and put them inside alpha nodes is, next come those beta nodes. Beta nodes resolve which WMEs actually satisfy this rule to get fired. To do that, B1 takes 3 inputs, this side, and this side. So from here it is getting 9, WME 9, 109 it is, okay, obviously. This is 4, and this side it is getting 6 and 7. And what it is comparing, that angular V value, whatever we took, right, for a win variable, we didn't give much focus on what values these variables are taking, right? So some angular V is there. So that angular V should be equal. That is what this beta node is checking. So 109, what was the angular V variable? It is C3. So 109, the win is C3, and for 104, it is again C3. Two working memory elements are coming from this side, 6 and 7. 6 has B2, 7 has C3. 6 has B2, 7 has C3. But this beta node takes only matching elements. So from all the directions, from this direction 9, 4, and 7. These three have a matching equal and V value. So these three get qualified to come down and sit in this F1 car rule. So this is a rule if they say. For this rule, these are the working memory elements that satisfy that. Similarly for B2, B2 is getting from 3 directions. One is 8, see, from this direction it is, okay, right here 8, and from this direction it is getting 2, 3. From this third direction it is getting 6, 7. What is it comparing? Again the V value. V is nothing but the win value of the win. So 8 has B2 as its value here. For win 8 has 2 has A1, 3 has B2, 6 has B3, B2 and 7 has C3. Again it, so oh no, 836. Okay, so 836 get qualified to come this side. Similarly for B3, if we see, we get 3 working memory elements, 101, 5 and 102. So all these are the rules along with the WMEs that qualify for these rules. Now comes the question of which rule to fire, and there are some metrics to decide on which rule. There are 2 which were given in the questions, like specificity and recency. Okay, let me clear this unnecessary. Okay. Okay. So specificity, the first one, specificity is total number of alpha nodes in this particular rule. So if I take F1 car, it has one, another, it gets inputs via this direction, and it gets inputs via this direction, and it gets inputs via this direction also. So in all these 3 directions, you need to count the number of alpha nodes. Here, alpha node is nothing but a rectangle or the check. 1, 2, 3 in this, 1, 2, 3 in this direction, 1, 2, 3 in this direction. So total, it has 9. So the specificity of this rule is 9. Similarly, for this one, if you see, it has 3 roads. All these roads have 3 alpha nodes in them, so it will be 9 for that. But for the last one, there are 4 roads actually. So this direction is one. Yeah, this is one direction. This is one direction, and straight, this is one direction, and this is one direction. So 4 different directions it gets inputs. So there was an advantage of another plus 3, so 12. So with respect to specificity, yes, yes. Yes, sir.
Maybe trivial question. If you are counting only the alpha nodes, so for this 5 and for example, 2 times you are calculating, no? So it should be less 2.
That was my question. That was my question too, but I explored in this course, they were calculating this way only. I don't know.
This way only.
Sorry,
Okay.
Naren, what is the question? Can you repeat?
For these
See,
2
for
directions,
example,
this first 2 alpha nodes are what is that? Repeating, right? So that was his question. This was one direction.
Okay, the way to think about it is you can
It is a set.
get to B3 using any one of those paths. So that's why you need to count only one, not both of them. See,
that madam explored and says discourse, they were saying you have to count separately.
There was some written like 12 or
so
something.
the way to think about specificity, I mean, if you just look at the English word itself, it's basically telling you how specific is the rule fundamentally. The more number of nodes you need to add to actually satisfy a rule, more specific it becomes. So that's the way I have been thinking about it.
Yeah, that is correct, sir. Murthy sir, you are right. But if they may not ask, but if they ask how many alpha nodes are there in rule 3, then what will be the number? It will be 12 or 10. For truck, alpha nodes will be 10 nodes are there if you count. If you take it as a set, because repeating elements in a set cannot be used, no? If it is a set, if you call it as a set, your class equal to power and win equal to V
It's
within
9, right?
angular brackets will be repeated twice.
It's
No,
9,
for
right?
HP greater than
for truck we are saying, not for this.
Truck.
F1 college.
For truck.
Yeah, for truck, how did you count 12? I just see 3 parts.
4
No, 4
paths are
paths.
there.
So 4 parts, yeah.
This is not clear.
But actually, it's not 4 parts.
No, this is 4 parts.
1, 2, 3.
There are 4 arrows.
Yeah.
Okay, that is where the confusion was actually. But that's okay. Yeah, we'll go with whatever we have right now.
Yeah, and ultimately, specific to this
that is
question,
an
okay,
advantage.
it is
See,
10 or
because
12, still it will be more
have
specific.
a record can be identified as a truck, right? If it follows the path class passenger A2, A6, A12, and A3, A7, and whatever that is at the bottom, I can't read it, A14, and A4, A8, and A16. So if these 9 nodes are satisfied, then it is a truck.
10 nodes.
No,
Okay.
that is B3 is nodes is only alpha nodes. So locations are only alpha.
Yeah. Right. A2, A6, A12, and A3, A7, this one. And
A14.
this also, A15 is also there.
No, it is not and there, right? It is or. Even if
Sir,
my record is only
under
one of them.
AO star, you don't confuse. Here it has to come. It has to be lesser than 300, greater than 300, and lesser than 500. Then only it will be a truck.
Okay, then it is less than 12, right?
Yeah. No, 10 it will be.
Yeah.
Okay, madam.
I'll check it.
Anyhow, for this specific question, 9 is both 9s are smaller than 12 or 10, so it can continue.
Right. So, obviously.
Okay, madam, please continue.
We continue. Okay. So for recency,
Please continue. Sorry.
how we will see is in terms of this number actually represents timestamp as they mentioned in the lectures. So the most recent number is nothing but the most highest number goes into which rule is what we need to check. 109 goes into this. So even if not 109, out of all these numbers, 107, 4, this and all, which rule has the latest record, that is the record with highest timestamp. So that rule will be qualified as per recency. So here 109 is the highest number. It is with respect to F1 car, so F1 car will be selected under recency. So these are the two approaches that we worked on in this data net. I think from week 11, week 10 only, these two are the concepts. Shall we move to week 11? I'll see again this. Yeah, week 10 we have only that rule based and data net. Okay, week 11 and 12 we are at this. Okay. So week 11, they proposed a new concept of trihedral object, which is nothing but an object which has exactly three planes at every vertex, three planes joining at every vertex. That is the definition of a trihedral object. For an exercise, I have a question here. Can you try out of all these four, which diagrams classify as trihedral objects? Hello?
What is the explanation behind it, sir?
I didn't get you. I didn't. Your voice was not clear.
Like the approach behind it.
Approach behind is at each vertex there should be three planes meeting
Okay.
at each vertex. That is what makes an object trihedral. See, for this image, if you see the right side, this is a trihedral object. If you see at this is one plane, this is one plane, and this is one plane meeting. Three sides give rise to a vertex. At every vertex, there should be three planes joining.
Got it. Hmm.
Okay, let me do that. In the first image, if you see at this particular vertex, this is one, and this is one. So this vertex is okay. There are three planes. But at this particular vertex, there are only two planes meeting. This is one plane and this is another plane. Am I clear in my explanation? Yeah. At this particular vertex, only two planes are meeting. This is one plane and this is one plane. So this contradicts with the concepts of three planes should meet to give a vertex. So A is not a trihedral object. B, as you see, there are three planes getting joined at every vertex. B qualifies. Again, C, for whatever vertex you see, there is an involvement of three planes.
In option B, there is one place where it is not three.
Yeah, yeah.
In fact, two of them.
Yeah. Not option C.
Actually, more.
Yes.
1, 2, 3, 4. 4 nodes don't have, 4 vertices don't have three sides or three planes.
So,
Which one? Can you give an example?
So, Naren, in B, option B,
which no B you are saying?
B.
I heard is B. Yeah, here it is fine.
triangle, right?
What
It
was
is
the
a triangle, sir. It is
Yeah.
triangle. Any point you take, there are three faces. If you have extended that as a pyramid and it stops at dot point, then that is not a trihedral. They have truncated the pyramid. So truncated pyramid is a trihedral.
Oh, I'm looking at the other way around. Okay. I'm looking at the inner nodes to be far away, not towards us.
No, don't take far away and towards us anything. Just let's see with the vertices and see if they are meeting. What is with D?
Madam, can you please explain the B1? Which are the vertices? Can you mark them so that?
Vertices are nothing but the points. This is a
Oh, I
point.
know how many are there. I want to see that. You only marked
This is
2,
a
but there are more
point.
than
This
2,
is
right?
the point. Yeah, there are more than two. It is in the back side. So this is Just like there are two here, there will be some other two corresponding these two. And there
Yeah.
is this one and there is this one.
Okay, so the all right.
Back also would look similar, right?
There will be 10 points in this, 10 vertices.
No, the thing is that in this there is no plus, minus, or arrows, right?
No,
No,
she is
no
not
Which
explaining
side
that.
is the material? You don't know which side is the
No.
material.
No need of material and all. I'm just asking if for each vertex there should be three planes joining. That's it. We didn't go till materials and all. Just see it as a 2D
Yeah, yeah,
diagram
got
also.
it.
Okay, so for C also the same way. If I take here, there are three. If I take here, there are three planes. Everything like that. So backside will also be same. If I take this point, one plane is here, one plane is here, and bottom is another plane. So that satisfies, right? D is not a trihedral object. Here, if you take, there are four planes coming. Actually,
See,
one,
if
two,
D the base is hollow,
which for C,
yeah, for B,
for B, if you're saying the base is hollow, no, not that. In that case, everything
yeah,
goes
it
wrong,
is
right?
not,
We
right?
assume, yeah, no, not like that. We understand that it is full. It is full.
Okay, because
Okay,
the
for
ED on the right side, it is chopped off, right? Okay, understood.
uh-huh,
Okay, I'm looking at the camera. Okay,
yeah. Hmm.
thanks.
Okay. So for D, it is not trihedral. We see there are four planes coming at the highlighted position. So this is not trihedral. So this is how we identify a trihedral object. I'm asking for the answers here. Okay, so only on this trihedral objects, our line representations, these line drawings work. For others, they do not make sense because this theory was proposed to work only on them. So with this background, we'll move to mark lines, mark junction names for this diagram. This is from our PA. Okay, how I approach is I start with this understanding. Whenever there is an arrow, material is on right. We keep walking in the direction of arrow, then material should be on right. That is one point. And there is one more discussion in our groups. We mark an arrow when material is on right, and we can't see all the planes. All the planes, we can't see any one or two. We can't see all three planes. At least one or two planes are missing for that edge. Okay, edges always have two planes. Okay, so a particular edge, we can't see all two planes meeting there. We can only see one plane. So in that case, for that edge, we mark an arrow in such a way that if we walk along the direction of arrow, material is on right. When do we mark pluses? We can see both the planes, and if we touch that point, if we assume that this figure is very sharp, and if we touch makes a cut to our finger, if we assume in that way, then we write a plus on that edge. Minus is similar. We see two planes, but if you touch, you can't get cut. So that is the basic understanding. So with this, let's first start where we cannot see two planes. See, for this edge, we are seeing that this is one plane. The other plane is towards this side, the bottom, the left side, there is another plane coming and making this edge. So we are not able to see both the planes coming here. So obviously we should mark an arrow on this. Arrow in such a way that if we walk, the material is on right. This is here. Similarly, the case is with this edge. If we cannot see both the planes coming. This plane we are seeing. The other plane is towards the right side of this image. We are not seeing. So arrow, when we walk along the arrow, material should be on the right. Okay, that is for this edge. Same is for this edge. We are not seeing the second plane. We mark an arrow such that material is here. Similarly for this, we are not seeing the second plane. This also we are not seeing the second plane. Second plane is basically the bottom of this figure. We are not seeing it. We are seeing only one plane coming at this edge, and we mark an arrow. That's it here also. We are not seeing the second plane, so we are seeing only one, mark an arrow. And what
The
else
MIT,
are there?
when I see you just this is called as boundary edges, madam.
Yeah,
What
yeah,
in
these are
MIT is
boundaries.
explaining
Yes.
is so
Yeah.
from 22 to 21, you keep on going in the boundary. So 21,
Hmm,
7, 7, 6, 6,
yeah, yeah.
9, 9,
Right,
25,
right. For,
25, 24, like that.
right. Yeah, yeah. This also. No, this is
No,
not a
no.
boundary. Yeah,
25,
yeah.
20 is not there.
Yeah, yeah. Okay. That's it. So, and then now this edge, we understand that this is an edge formed by this plane and this plane, and we are seeing both the planes. And if we touch here, we get cut if the object is sharp. So that means this edge is protruding out. So we mark it with a plus. Similarly, here also we'll get a cut. This edge is a plus. This edge is also a plus. This is also a plus. This is an edge, right? So we are seeing both the planes. Again, this is an edge. This is one plane. This is one plane. We'll get a cut here. So this is a plus. This is a plus. For this, we are not seeing the other plane that it is forming. For this edge, we are seeing this is one plane. The another plane is under this image, and under this. So we are not able to mark a plus here. This is this way. Similarly, for this is this way. Not able to mark a plus because one plane is here, another plane is in the bottom of the figure, in the bottom of that beam. Okay, for this edge, there is a plus. This is an edge and it cuts out finger if we touch and if it is sharp. Similarly, for this plane, for this edge, this is one plane. Another plane is in this direction towards the down. Like this, there is another plane. So again, there is a this thing. For this, we are able to see both the planes. This is one plane, this is one plane. So this is a plus. For this also, we are seeing both the planes. One is this, one is this. So this is a plus. This, we are not seeing.
Which one, madam? 3, yeah?
No,
1,
4,
3 edge.
4.
You talk about 1, 3 edge?
1, 3, I didn't mark it. 1, 3, we are seeing both the planes meeting. We see that it is a corner, it won't cut us, so we put a minus there. Same for 16, 17, it is a corner, we see both the planes, it won't cut us if even if we touch it, so it is a minus. But this 10, 11, it cuts us, it is a corner, it is protruding out. 8, 15 is
14.
also a plus. That is done. So 13, 14 also is a plus. 17, 13 is also a minus. It is a corner that is inside these two planes, and it won't. 11, 17 is also a minus. Any other edges pending? No. We have figured out all this.
21, 18, and 25, 20.
25, 20.
21, 18, yeah, yeah. 21, 18, we are seeing only one plane. So we are not able to see the other plane. It is in the back side, this direction. The other plane is there. So we put an arrow there.
25, 20.
Okay, 25, 20, anyway, like this. Okay, so that is with respect to marking. Then we come to labeling. That is simple. We take help of this already given labels and we give accordingly. For
Just something which I'm always confused about, like how does the direction of an arrow is decided?
yeah,
Like, is it
yeah,
random or you can put any direction?
no, arrow is, you are asking about how do we put or how do we relate with respect to the given figures?
The direction of the arrow.
Yeah,
Like
arrow is, if you keep walking along the arrow, whatever material that you are seeing should be on your right side. You walk in that direction, you put an arrow in towards that direction.
Can it be in the opposite direction?
No, this is a standard that they followed. You see, if I walk along this edge, which direction should I walk so that whatever plane is visible will be on my right side? This material should be on my right side. So,
Understood.
which direction?
Understood. Yes.
Anyway, I decided that it is an arrow because second plane is not visible.
Yeah.
When it comes to direction, this should be on your right. So you should walk in this direction. Only then it will be on your right, right? Okay.
Got it.
Okay. So this is with respect to the labeling. Maybe we for numbering as for the vertex labels, we have the diagram. Okay, we go to some another figures that we have in one of our practice assignments. This is simple. They ask for labels of this vertex 1 or 2. First of all, we'll see why it is not Y and T edge. There is always a confusion because 3 arrows are meeting in this and 3 arrows are meeting this in this also. But in T edges, 2 of the arrows of 2 of the lines are the same. They are not 2 lines actually. This is a single line. But in Y, this is different, and this is different. These are 3 different lines coming and meeting. But for T, it is a single line meeting with some another single line. So in this, it is not to be confused of a Y written like this. It is actually a T where this is a single line. That is to be understood in that way. This is a T. Similarly, this is a T with like this, not a Y of this is one, and this is one. No. Y always have all 3 pointing in different directions. So with that understanding, we'll first try to map this T. How to map this? For all the T's, if we see for the top, this line, you stand on this edge, which is separate from the north. These 2 lines are equal, we said, right? So we stand on the third edge or the second edge and look towards the junction. Then these arrows go from right to left. That is the understanding. For any T, if you stand on this branch, let me call this is a trunk and this is a branch. So if this is the branch, you stand on the branch and look towards this junction, then arrows should go from right to left. So in that case, this is the branch, stand on this branch, look towards the junction, arrows should go from right to left. If you see from here, this is what right to left shows like, feels like, right? Of course, for us, it is from left to right, but stand here and look towards the junction. Similarly, for this T, you stand on this branch, look towards the junction. So in this look in this direction, arrows should go from right to left. So there is an inconsistency. Even though this is the same line, this vertex 1 says that I should put arrows in this direction. Vertex 2 says that I should put arrows in this direction. So because of this mismatch, there is no possible labeling for this graph. Am I clear in conveying? Okay. So similarly, this is not a Y junction. This is a T junction. This is a single line actually, and this is a branch coming out of it. So with that understanding and with our earlier point, we stand here, look towards the junction. Arrows should go from right to left. So this is how our arrow should go if 2 is a T junction, given that 2 is a T junction. Now, 1, we know that we can clearly see that this is a W junction. There is something like this. Of course, it is given in an inverted fashion. This is the junction. There are all 3. This is the center edge. So for 1, we need to decide the label. 2, this we will figure out later. But for this line, we are sure that it comes towards the junction. So the center line is coming towards the junction in a W edge. Is it there in any of the W edges? No. In no W edge, the middle line has an arrow, that too coming into a junction. So this is infeasible. Again, this drawing doesn't have a proper labeling. W is not possible here. And this one, always T is the easiest one to mark. We see that this is a T junction, as we see. Stand on the branch, look towards the junction. It should go from right to left. This is clear till here. We need to figure out other labels to decide on what should we give to this branch. Is it a arrow or is it a plus, minus, something like that? What should we give on this 1, 4 line? That will come one by one. Here, once we have this label, we come to 3 and we see that 3 is an L junction. This 3 is an L junction. We have L junction labels here. Yeah. So for an L junction, if you stand in the point and look in the middle of both the junctions, so this is your left and this is your right. This, if you stand and look in this direction, this will be your left and this will be right. So it is like stand and look into the intersection, towards the place between both the edges. This will be left, this will be right. So look this side, this is left, this is right. So with that understanding, so look towards that, this is your left, right. So I'm looking towards those, this is left. So left one is coming into the junction. What do we have? Where do we have such cases? Left is coming into the junction. So L4 is one option and L5 is one option. We can do anything. L4 is also possible, L5 is also possible. Okay, if I take L4, let me remove this R. Okay, if I take L4, what will come to my this one? It will be like, I should write like this. But what happens? It breaks at 2 with the same reason. 2 is a W junction. In the center one is a edge that has an arrow inside. It doesn't satisfy any W's. So I should not take L4 here. L4 should not be taken. I will take L5. Okay. So don't take L4. Don't write this arrow. Right with respect to L5. L5 is left is coming inside and right one is a plus. So this is happy for us. W has a plus in the middle. Again, it has 2 options. That's okay, we'll see. So it is feasible to, suppose I am given this is with respect to vertex 3. With respect to vertex 2, we saw that middle is a plus. So obviously it will be W1 and W2 will be both the options. If I take W1, so the left one, again stand here and look in some direction, fix some direction which suits you so that left and right becomes easy. So if I look in this direction, this is my left for W and this is my right for W. I stand here and look in this direction. That means the direction of the middle edge. This is my left, this is my right. So when the middle is a plus, left should be outside the junction. It should go out of the junction. That is what W1 is saying. When the middle is a plus, your left should go out of the junction. So middle is a plus, look towards this direction, left is out of the junction, right is into the junction. Left, right convention. Now this is clear. This is a Y junction. No confusion. The right side arrow is going. So we identify that this is a Y1. Left side arrow, it should come here. It should give me a minus. So this is a T with the branch having minus. This is T4. That is the answer. What if we put, this gave me T4. What if we put W2? W2, if we put, this would have become minus minus. This both would have become, okay, confusing. W1 gave me T4, that is clear. What if I choose W2 for 2? That means this is, what is this I wrote? Plus. Okay, W2 means other 2 are minuses. So I fix my 2 to be W2. In this case, Y has a minus here. So in the top 2 nodes, Y minus is only Y2 possible. Again, minus, minus. That is a label. So in that case also, this T junction vertex 4 is a T4. So even if you take W1 or W2 in 2, it is giving a T4 in the vertex 4. So that's why it is the answer that is possible. Only the only answer that is possible. Is this clear till now? Any doubts? Shall we move ahead? We have so much to discuss. Okay. Then, is it all about week 10? No, week 11. Yeah, week 11, we saw line diagrams, and then there is model-based diagnosis. There is one concept. Here, the basic understanding is simple. Few blocks or whatever you say, components are connected, and their functionality is given. Few are meant to do a multiplication. Few are meant to do addition. So, if the whole model is working properly, and if inputs are given like this, there is a 1, 2 here. This is M1 is expected to do a multiplication, so the output is expected to be 2. 4 and 5 are going into M2 and output will be 20. Expected output is 9. That's how these blocks work. M3 is a multiplication block. A1, it takes inputs and adds. So 22 is the expected output. 20 and 9. So 29 is the expected output here. We see that only this 9 is being fed twice to A3. So this is 18 expected output. A4 is again an addition. It takes 22, 29, 51. And 29 and 18, it is 47. So that is how this model should work. Expected outputs are for 51 and 47. Then there is this concept. What happens if some or a few blocks fail out of all these blocks? If something fails, what happens to the outputs? So for that questions, for that concept, I have two questions. It is given that, let's see, this is the first question. It is given that out 1 is 20. Out 1 is giving a 20 and out 2 is giving a 47. So in that case, what component would have become faulty? That was the question. To do this, out 2 is 47, which is same as the expected. So out 2 is working properly. Out 1 expected is 51, but 20 is coming. So out 1 is getting a wrong answer. Right? So first of all, let me write like this. M1, it influences, its value goes only this way and it influences out 1. M2, its value goes via this way also and its value is being fed this way also. So it influences both out 2 and out 1 also. Clear, right? So M2's value has some direction into out 1 also, it is going into flowing into out 2 also. So that means if M1 is broken, there will be something wrong in out 1. But if M2 is broken, you will see wrong outputs in both the ends. So that is the understanding. M3, its value is being again fed to both out 1. See, with this arrow, it goes upwards. It is going to A2 and then it is going. So it has some connection into out 1 also. It has connection into out 2 also. Similarly, right, for A1, it impacts out 1 only. A2 impacts both out 1 and 2. Both it will impact. If at all A2 is failing, both your outputs will go wrong. A3 is failing, only out 2 it is impacting. Okay, A4 is failing, obviously out 1 alone. A5 is failing, out 1 alone. So in the given question, we see that out 1 is getting only affected, out 2 is not getting affected. So which are those cases? This is one case, this is one case. No, okay. This is one case. If only one component is faulty, then what it could be? So M1 is impacting out 1 only. So M1 can be the single component, A1 can be the single component, A4, if A4 fails, out 1 fails. A1 alone fails, out 1 fails. M1 alone fails, out 1 fails. So these are the 3 components that can go faulty on their own to give this wrong output. That is the answer. M1, A1 and A4. Similarly, can we do for
here the catch is if only one component is faulty.
Yeah. Only one component is faulty. If they ask two components, that will be different, but I don't think they'll go that deep.
Just
If
I'm just
this understanding, yeah. One component
just
means single component which affects out one alone directly. Yeah. So can we do for out
just
two?
for completion. I told madam.
Yeah. Yes, can we do for out two? What one this second question. Out one they are getting 51 and out two they are getting 37. This means out one is matching the expected value, out two is wrong. So out two is alone fails means which component alone could have gone
A3,
faulty?
A5.
A5.
A3, A5.
Exactly. Yeah. So that's the answer. A3, A5. That's how we do this. Okay. So there's nothing much I could pick in model-based diagnosis. Okay, then is
Can there be
yes.
questions asking us to actually change the input, find the right inputs?
Can be. I don't know. That is our luck.
That's the real problem.
Yeah. That's like how they used to ask in that one, no? What is it? Game trees.
Yeah.
Which node will you change? Which min max will
Yeah.
change to get so and so? Yeah. Okay.
Then we can spend the entire time doing just that.
Yeah. Okay. We'll move ahead. Then this is the last concept. We'll finish soon. CSP, as it is easy to understand, it is a combination of both reasoning and search. That is, we try to find values that satisfy the given condition, but while doing so, we don't go in a blind fashion. We go with some reasoning. Basically, any CSP will have a representation like this. It will represent what variables are included in it, or variables are being worked upon, and each variable will have a domain. So domain is nothing but set of possible values. Here we have 1, 2, 3. So I took some casual examples. And then there will be a set of constraints. Constraint is nothing but a relation that should be satisfied while finding the solution. So this RAB is a relation imposed on A and B variables. It has this set of values. So this means if A is 1, B is allowed to take 2. Again, another value is if A is 1, B is allowed to take 3. So this means that. This is it. And this means if A is 1, B is allowed to take 1. So this entire C1 says AB combination should take only these 3 values, like 2, 1 and 2, 3 for AB are not allowed. That's what it is trying to say. That is a constraint imposed on A and B. Similarly, they have constraint on A and C. They should be taking these values only. They don't have any constraints on B, C. That means we are free to choose any combination of values for B and C. It is not undefined basically. It is a universal relation. We can choose any value for B and any values for C. Okay, so while again for each constraint, it has scope and a relation. Scope means on what variables it is defining or it is imposing a constraint. For C1, the scope is A comma B. That means this constraint C1 is imposing a relation or a constraint on A comma B variables. So A comma B belong to scope of C1. Relation is nothing but all this. What is the thing that it is saying? What should A and B follow, or what should A and B stick to? So this is relation. So similarly for C2, the scope is A comma B, A comma C. We have a similar relation. So such constraint whose scope is a two variable set. That means this constraint is on two variable only. So we call such constraints as binary constraints. There can be others also. No? So like RABC, I can write. It imposes condition on all ABC. It should look like 1, 2, 3 or 2, 1, 2, something like that. It should look like this. So this is whatever, some other constraint. I don't know the name. So for two variables, it is a binary constraint. Okay, there can be unary constraints also. Let's say, suppose B, it will take only 2. This is that even though B is allowed to take, well, B generally takes 1, 2, 3 variables. For this particular problem, I want B to always take 2 value. So this is a unary constraint. Such constraints are also possible. Okay, so we find a solution keeping all these constraints in mind, and we arrive at values. There is one small question I could pick. Which of the following are necessary conditions that must hold for a CSP? Can anyone try this? It is saying all relations are nothing but these. This individual, whatever they have put. All relations should hold at least one, more than one.
All relations in all constraint must not required, no, madam.
the
You are
second
not
one.
telling the answer now. All
The second one, right?
constraints, all relations in all constraints must hold. At least one relation in all constraints. No, I think first one is more than one relation in all constraints must hold. I will go for one.
Maybe all relation in at least one constraint must.
At least one relation.
People tell means the answer will come,
All
but you have to
constraints
give reason.
all constraints must
No, it is in my view, it is at least one relation in all constraints must hold. See, because that's from the relationship set in the constraint, right? Even if one of them is satisfied, it should be fine.
Right.
But there are multiple constraints, so you have to satisfy all constraints. So
yeah, you have to satisfy all constraint individually, but inside a constraint, one relation is enough. So I can take 1, 2 from here, 2, 3 from here, and propose a solution. So A, B, C will take values 1, 2, 3. So I'm satisfying this 1, 2. I'm satisfying this 2, 3. Okay, neglect this. I just wrote for unary constraint. So this is a valid solution. Obvious that when 1, 2 is satisfied, 1, 3 will not be satisfied, right? So it's obvious. At least one relation in all constraints. I cannot just leave if at all some BC is there. I cannot leave it without taking anything from there. I should satisfy all conditions, and inside that, we should take at least one relation which satisfies. I should pick any one from this and build my solution. Is this? No, I did this with some other app.
So I guess the idea is that all constraints have to be satisfied.
Yes.
Now, when you
all
look at the
constraints.
constraint, even if one of the relationships satisfies that constraint, you're good.
Right. All constraints must be satisfied. Inside constraint, whatever it gives some options, you pick any one option, at least one option from that, and you're good to propose a solution. Okay, one brute force approach of finding a solution is backtracking. Like from all the domains, suppose A, B, C are there. Start with exploring A as 1 and B as 1. Put C as 1. Is it breaking anywhere? Yes, no. No, it's not breaking anywhere. AB 1 1 is okay. AC 1 1 is okay. Right. So then you explore 1 1 2. Is it breaking anywhere? Yes. AC doesn't have a valid combination of 1 and 2, but I'm having a valid combination. So this is not great. Something like that. So you explore all. If you break 2, is it because of 2? Okay, go back. Change it to 3. Will it follow? No, it doesn't have. So something like that. You keep on doing backtracking. Something is failing. Replace this with something else. 1 1 4. If 4 is there, something like that. So this is a plain brute force approach, which is called backtracking, and we understand that it is very time consuming, and we aim to find out methods that make this task easy. Okay, then there is this concept of matching diagram. Matching diagram is nothing but whatever the constraints or the values that they give in this form, we put into a diagram so that each node is a variable. Inside that, we put the values that it is allowed to take, and this will become the edges. That edges are nothing but the possible values. So R, AB means 1, 2 is allowed, so this is an edge. A is 1, B is 3 is allowed, this is an edge. 1 1 is allowed, this is an edge. Again, AC 1 is a load, this is an edge. Okay, for time being, think this is BC. This is bad. Okay, so BC, if it is 1, 2, 3 means this is an edge. So this is what a matching diagram looks like. It puts all valid options into edges between the nodes. What happens? So this straight away exposes some inconsistencies that A is not allowed to take 2, 3 because A and B are connected, but when A is 2, B is not allowed any value. There is no value available for A B connection if A is 2. So that is nothing but we do this functionality we do in the revise AB. What it does is removes 2 from the A. The A is nothing but domain of A because I am revising A. Revising A means changing A with respect to B. I am taking B as reference and I am changing A. So taking B, there is nothing, no way to for 2 to go. So change 2 and removes 2 and similarly it removes 3 also from here. So this is what they mean by revise AB. It changes the domain of this first variable. Okay, with this approach, AC1 is an algorithm. What it does is it does repetitive revisions on this. It takes every pair like AB, AC, BC, something, every pairs, and it does in both sides. AB, it do A comma B, revise of A comma B, and revise of B comma A. Similarly, AC does revise of A comma C and in the opposite direction also. So revise of C comma A. So this keeps doing all this. Revision continuously eliminates values which do not have a link to the connected variable, right? So till when this continues, even if there is a domain change, even if a single value in any domain gets deleted, the whole process gets repeated. Suppose A is here, B is here, C is here. There is some D which is connected like this to A and C. Actually, the change in domain of B doesn't impact D. Even if one value gets deleted from B, D has nothing to do with that. But AC1 just brute forcefully does all that. It does for AD, does for BD, does for CD, everything it just repeats. So this problem they are trying to overcome with the another algorithm called AC3. What it does is, okay, suppose A, B, C are connected in this way. When B is impacted, it will impact either A and C only. D is anyway not going to be touched, right? So it won't take this D for revision. This can be understood why a revision in B impacts A and C. We can understand from this kind of diagram. A has say 2 values, B has 2 values. B has 1 and 2, C has 1 and 2. Okay, A is having this relation. Okay, so when you go from left to right, you just revise A with respect to B. For A, there is no change, everybody are safe. And then you are just going ahead, revise of B comma C. You see that for 1, there is no connection in C. So this 1 gets dropped. When this drops, although you have came ahead from A to B, but this is impacting A also because now this 1 has become a variable that doesn't have any connection into B. So you should need something to go back and change this domain also. When this is pruned, this also will get pruned. So that is what I meant here. When something is changing, there will be some impact on the connected variables. So that is what these arrows mean. There will be impact only in the corrected variables. If there is somewhere D sitting here, it doesn't get impacted by this change. So that point, AC3 is considering and it does revisions accordingly. AC1 just does all in a looping fashion. There is some time complexity, etc. for AC1, AC3. I think you can go through those theories on your own. Okay, then another one is there are two concepts of arc consistency and Path consistency. Arc consistency is nothing but every pair of variables should have edges possible between them. Path consistency is nothing but you should be able, it takes 3 variables should have edges to make a triangle. Arc consistency is nothing but after all these revisions, there should not be any gaps like this. There is no connection from one to here. So remove all those gaps. B should be connected to A, B should be connected to C. And again, A should be properly connected, this also. So all should be properly connected. There are no gaps between any pair of variables. That is what is arc consistencies. So is this graph arc consistent is the question. This is node B, this is node C, this is E. They have values inside R and B. So this is the domain of B. This is the domain BGR. This is the domain of C. It has B and R. They mark the edges. Here we see D has a proper connection towards this side and this side. C also has proper connections towards this side and this side. E also has proper connections towards this side and this side. So every variable has values for every BGR in E has connections in both the directions. I messed it up. For every variable. For this B, it has both the directions connections. R also has. Similarly, this has in both the direction. This also has. This also has. This also has. So that is what is meant by arc consistency. So this network is arc consistent. Then we are checking about path consistency. Are there?
No.
Someone has raised a hand. You need not raise hand. This is one second.
So each pair needs to be connected in both the directions. Each variable needs to be connected in both the directions for arc consistency.
Each variable has to be connected to all the available other variables. If there are 4 variables,
C has no need of connecting to all the variables. C has relations with D and E, right? C is related to D and E. So every value in C should have some connection with D, some connection with E possible.
Okay.
Okay.
It can connect to any one variable of the other class.
Anyone. Yeah, see, from B it is connecting to only R. If B is not B, B is not going to B. Obviously it will not because there is a not equal to sign, right? So it is not like B should be towards all, we should not like n into n, nothing like that. Every value in C should have connections towards which and whatever variables it is interacting with. E is having connection with C and D. So every value in E should be holding some relation into those. Right. So in our earlier example, it was not the case. In this example, if you see, A is 1 to this one I wrote, no, 1, 2, this is 1, 2. If you draw like this, A, B, C. If we draw like this, B is connected to A and C, but this value C, it is connected to only A. It is not connected to C. It doesn't have it this second side, no?
Got it.
So that's why this is not arc consistent. To achieve that arc consistency, V1 and AC3, they ultimately prune this. And again, they prune this because this is lost, so that we achieve arc consistency. Now it is arc consistent. You see the graph now?
Madam.
Yes.
Madam, one doubt, madam, here. If there are 3 variables, then 2 edges will come. If there are 4 variables, we need 3 edges, no, from each.
That depends on your relation. That depends on your relation, no?
Yeah.
If there are 4 variables, my constraints do not impose on anything, no? See, if I have like this, I can still have two edges.
Yeah, that's what I meant is, can we have 3 edges also? If the constraints are like that.
If this is the graph, every variable inside A should have a relation to D, B, C. Again, this should have 3. That's what
Okay,
is R
okay.
consistency.
Okay, yeah. Thank you, ma'am.
Okay. So next comes every pair of connected variables. Not every pair of variables, connected variables. Okay, path consistency means if you take any edge, it should be allowing us to form a triangle. Suppose if you take this edge, will it allow me to form a triangle? It will go till here, closed triangle. But from R, if can I come back to R? This no, not possible, right? Because that is not given. That edge is not possible. C and D cannot be same. So what happening? This edge is not getting extended into a triangle. This edge doesn't extend into a triangle. Similarly, this edge, if I go this direction, I cannot come here. Okay, even if I go like this, R to B, and again I cannot come back to B. So this is also not getting extended into a triangle. There are only few edges that allow us to complete a triangle pattern. So those are these edges. R, you can go to G, and from G you can go to B, and B. This is a triangle. Okay, and another is B. You can go to R. You can go to B. No, not this.
Madam, that is not there.
There is one more.
B,
Yes.
BGR. One more BGR is there. Left side
Yeah.
B, in
B,
between center is G
Yeah.
and B.
Yeah. This is how we can extend to triangles. You see that this R in E is not allowing us to form a triangle. If you go to B, you go to R and you get lost in some space. If you go to B, you go to R and again you get lost in some space. So this R in this is C, this is C, this is variable T. This is not allowing us to form a triangle. So to achieve path consistency, we delete this R. But if the R is not there, path consistency is not there. So this will be removed. There is now no these edges. Right? Similarly, B in E is not allowing me to okay, this R, it is not allowing me to form a triangle. So take off that R and remove its edges. Then E, this B is not allowing me to form a triangle. Take out that B and remove those edges. Others are fine, right? Others are allowing me to form a triangle. This is what achieving path consistency means. So the question is, after CSP is made path consistent, what tuples will remain in the relation RCE? Earlier RCE has how many edges? 1, 2, 3, 4 edges. It is like B to R, 1 is there earlier, B to G is there, and RG is there, and RB is there. Right? C has 4 relations earlier 1, 2, 3, and 4. After achieving path consistency, how many are there? What are they? Is the question. Okay. This is the answer. After achieving path consistency, we removed BR we removed, and this RB we removed from CE. I am talking from C to E. B and R we removed, and RB we removed. So only BG is present, RG is present. That is the answer here. After achieving path consistency, only these tuples will remain in this RCE relation. Is this clear till now? Path consistency and how we achieve that?
Yes.
Clear now.
Yes. forward checking. There is this last concept of forward checking. So we saw how we achieve app consistency and how we achieve path consistency. There is one more algorithm. What it does is it sees into future. Like our revised algorithms, it was seeing for pruning how they are doing. Similarly, this forward checking prunes the domains of future variables also. Revise was like when revise of B, C is there, it is checking C and it is revising only this B. To if this B is connected to some D, I need another some revise option of D with something else. So in this step itself, it is only concerned with altering this B. It is not going ahead and deleting its neighbors. That is being tackled as a different operation. But what forward checking does is it sees one step ahead earlier. Okay, if I take this decision now, in my next step, what could be possible? It is similarly like our Sudoku. When if we place a 5 or number something here, we can cross other variables, other cells, right? We think that 5 will not be here, 5 will not be here anymore. So this helps our decisions, right? We do this while solving Sudokus. Okay, so that is nothing but a forward checking. So forward checking always needs an order to be given in which we should explore. Suppose the order is here, go with A, B, C, D, E, F. In this diagram, go in this order, keep exploring and do a forward checking. We'll see how that goes. We have these domains given. A is BG, B is G, C is RBG, D is RG, E is B, F is BG. Okay, these are the domains given here. The algorithm tells to go in this fashion. So first I'll go to A and take one value. Suppose A is B. If A is B, what will be the look ahead, like forward assumption that C cannot take B? That is the change it does. When A is assumed to be B, it removes this B from domain of C. Okay, I'm done with A. Only once, only to the neighbors, not since B is removed, go there. Since that is not like that. Only one step ahead, only to the immediate neighbors. It will prune the domains and remove the values that are not possible. Okay, if A is B, I will cut off this one. A is B, taking B for A is a general assumption, like our move gen function. Then go to B. B doesn't have any options, it is G. So if G is taken, what will be the next forward C? That this will be gone. That is what is happening in time step 2. I took one value for B and pruned its neighbors. Similarly, for D also it will take out. So if I take B, I cut off G from here and here. That's what is happening at time step 2. Then they are asking me to give value for C. Okay, C is having R. So I have no other option to select R. Immediate neighbors, A is not impacted, F is not impacted, B is not impacted, but D is impacted. D will lose R because C is R. Here all the edges are assumed to be not equal, right? When C is R, D should not be R. D has lost. But what happened? D has lost all its values from its domain. So that's where is the need to backtrack. So we undo the recent operation. Just now I striked off this R, right? So I undo that R. Okay, I undo that striking operation and I undo choosing R for C. I will try another option for C. That is how backtracking, because this is not working, right? If I take R and I had to strike off this R, so I undo those. Okay, I have to take another option for C, but there is no another option for C. So I backtrack to B. Backtrack, what happened? At B, I took G and crossed these two, right? So I undo the previous operation. No, don't cross G. So this is my previous operation. Take another value for B. But B also doesn't have another value to explore. Undo. Backtrack to one more step towards step. Okay, so what was at A? Backtrack. Don't allow this selection. Take a different selection. Okay, if you find another value at B, that is okay. But you keep undoing till another possibility is present. Okay, take G for A. So now we prune G here. Okay, now again we started. A is over. Then we come to B. B has G. Okay, I take G for B and G is already gone. G is gone. So my time step 2 also happened successfully. Come to C. There are two values. I randomly take one variable, cross this. Again the same problem, right? I took R and I crossed it off. So there is some wrong. I need to undo that. Don't cross this R, don't take this R. Now I have another option in C possible. So I'll go to that. Okay, if I take B, then take out this B. This R is safe now. Take out this B also here. C has connections to the sides, right? So that's it. Okay, C is safe. Nobody went as an empty domain. Then D. D has only one variable R. Okay, strike out from C. D is also done. Everybody is safe. Then move to E. E has only one variable B. Okay, B is already striked off from it. So that also happened peacefully. And F has only one variable for G. So this is the answer. A will get G, G, B, R, G, B. So this is the solution. This is how forward checking works. It just takes a value, prunes its neighbors if there are inconsistencies. Somewhere if what that variables get an empty domain, undo our recent last operation till you are able to find a new value and switch to that option. That is how it works. It had to undo in the middle and again. Here luckily we have another option for this, so we went with that. That's how forward checking works. I think this is the last topic in our week 11 and 12 together. 12 doesn't have much. Yeah, this is what is discussed in look ahead section. Is this clear?
Yes.
So that ends my plan for this discussion, and I'm on time this time. 7 o'clock. Okay, anything else that we need to discuss, or we can close this session? Okay. Okay. Thanks everybody for joining. Once the recording link is available, I'll share in the group. Thank you. Thank you, everyone.
Thank you for the session.